All right, so this is the first problem we're doing that's going to put both parts that we learned yesterday together. We have a pebble being dropped into a calm pond, or maybe you threw it out into a calm pond. I'm sure we've all done that before, and just kind of watch the ripples go. So you can kind of picture that scenario going on in your mind. The ripples are in the form of concentric circles. So you get more than one ripple, and they are all circles. When the radius r is increasing at a constant, with the radius increasing at a constant rate of 1 foot per second. So these waves are propagating over the surface of the water at 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So the wording in this problem gives away the formula that we're going to have to use in this problem. What is the formula? The area of a circle, right? We have area, total area, so we're going to need that. And we're talking about concentric circles right here. So A equals pi r squared is the formula that you're going to be using. So I want to write down what I know and what I don't know. First of all, is area constant? No. Is the radius constant? No. So those are my two variables. I'm going to draw a picture here. I have a circle. I have a radius, r. And I'm going to label some stuff on this circle too, or maybe I'll just write it down off to the side. They tell me that the radius here is 4, so I'll write off to the side, r equals 4. Because it says when the radius is 4 feet. The radius increases at a constant rate of 1 foot per second right here. What is that? It's not acceleration if it's a constant rate. So that would be what variable? So it's dr over dt. The rate of change of the radius with respect to time is 1 foot per second. That's dr over dt is 1 foot per second. This is 4 feet. Okay. What's A? So how could I calculate area if I needed it? So yeah, you'd square the radius and then multiply times pi, okay? So we could figure out A if we needed it, but there's something else that we're going to have in this equation. That guy. The rate of change of the area with respect to time. And it turns out that that's what we're looking for. What rate is the total area of the disturbed water changing? That's the guy we're looking for. So once we take the derivative of this equation, this formula that we're working with, we'll have to solve for dA over dt, and that's what we're going to find. So we're ready? Take the derivative of that. What do we get? dA over dt. We're taking the derivative of both sides with respect to time, so we get dA over dt equals 2 pi r dr over dt. Remember, you have to differentiate implicitly because the variables here do not agree. We are taking the derivative with respect to time. So every time you take the derivative of a variable, you have to include a d, that variable, over dt. So that's the derivative. We are looking for dA over dt, and dA over dt is already sitting here all by itself. We have information for all this other stuff, so we can just plug it in. We have 2, we have pi, we have a radius of 4. We have dr over dt, which is 1. So that becomes 2 pi times 4 times 1, which is just 8 pi. And we need to come up with some units here. This was just a 2, this is just a pi, but this 4 is feet, and this 1 is feet per second. So you multiply and you get feet squared per second. Feet squared, of course, is an area unit, and then per second gives you a rate. So you're changing at a rate of 8 pi feet squared per second. All right, next problem. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. So the first thing I want to do here is draw a picture. It's pretty tough to draw a picture on a flat surface of a three-dimensional object, but for a sphere, what I like to do is put a little window on there or something that shows some sort of dimension. Yeah, so now you can kind of picture, like I can kind of picture a little better the fact that this is supposed to be a sphere, despite the fact that it's like lopsided. So there's going to be a radius to the sphere, and since I'm dealing with a sphere, and I'm talking about cubic feet tells me that I'm dealing with what? Volume. And if I'm talking about a sphere, then I'm dealing with the volume of a sphere. So I probably need to know what formula for the volume of a sphere would be. What is the formula for the volume of a sphere? You know what? I bet it's in your book. You could probably look in the back cover, maybe the front cover. 4/3 pi r cubed. You won't be able to use your book on the test, just in case there was a volume of a sphere problem on the test. You would need to know that one. This is one that you should know anyway. It's frequent enough that you should know it. Okay, so let's identify some variables here. We have V. Do we know V? Don't know it. We have R. Do we know that one? It says when the radius is 2 feet, so we know that one. Okay, there's no more variables in the actual formula, but when I take the derivative, I know that I'm going to wind up with a dV over dt, and I'm going to wind up with a dr over dt. So, do we have a dV over dt? First of all, what does dV over dt mean? Yeah, it is the derivative of volume, but that is the derivative is a rate of change. Okay, so this is the rate of change of volume with respect to time. Do we have that information? Actually, we do have that information. It's right here. Air is being pumped into a spherical balloon. Okay, air has volume to it, and we're pumping it in at a rate of 4.5 cubic feet per minute. Okay, so it's right there. That's dV over dt, 4.5 feet cubed per minute. Find the rate of change of the radius. What is that? That's dr over dt. So this is what we're looking for. We don't know volume, but we probably could calculate it if we needed it. But when we take the derivative, we won't even have v left in the equation, so we don't need it. Okay? All right, that's all the stuff we need. And now we kind of know where we're headed. We're looking for dr over dt. dr over dt is going to wind up over here when I take the derivative, which means I'm going to have to solve for dr over dt. That's no big deal, actually. You'll see. So take the derivative. What do we get? Equals? So yeah, the 3 comes down, and the 3's then are a fancy 1. They're gone, and I just have 4 pi r squared dr over dt. All right, that's the derivative. Now I just need to get dr over dt by itself. So to do that, I'm going to divide, obviously, both sides by 4 pi r squared. But I'm going to write that like this. 1 over 4 pi r squared dv over dt equals dr over dt. What that does for me is it allows me to see that I have this math going on right here, and then I'm multiplying times dv over dt, which I know, okay? Don't try to put everything in like one common fraction or something like that. Keep them separated out. Okay, so I can substitute stuff in. I have 1 over 4 pi times r squared, so 2 squared, times dv over dt, which is 4.5. And then simplify that down. I'd get 1 over This is 4, so that's 16 pi. And now this 4.5 is like 4.5, which is 9 halves. So I'm going to write that as times 9 halves. So I get 1 times 9, which is 9, over 32 pi. And then my units here, if I have dr over dt, the change of radius is feet. dt, in this case, is minutes. So this is going to be feet per minute. 9 over 32 pi. Yes, you can go to decimal there, but the answer in the back of the book is going to give you this as your answer. We always prefer exact answers unless we're trying to tell somebody what this is. I have no idea what 9 over 32 pi actually is. It's probably about like 0.1. So 0.1 feet per minute is the rate of change of increase of that balloon. All right, so we have an airplane that's flying on a path that will take it directly over a radar tracking station at an elevation of 6 miles. There's key words in here that will lead you to how this picture is supposed to look. It says an airplane is flying, great, on a flight path that will take it directly over a radar tracking station. So that is the key phrase that you need to see in order to understand that if this is my radar tracking station, my plane will fly over it, which means it is not currently directly over it. So I'll draw a beautiful airplane with all of my airplane drawing skills, which you don't need to do. I'll put a little shark face on here because it's a mean airplane. All right, so that airplane is flying this way, right? All right, eventually it will get directly over the tracking station, which is an elevation of 6 miles. Then it says, if the distance s from the tracking station to the plane, well, that's not this here, that's this. And they called it s. And it's decreasing at a rate of 400 miles per hour. That's a good thought. All right, so we have 6, we have s. Do we know how far away the plane is, like horizontally, from the tracking station here? No, we don't. Okay, so when s equals 10, though? So we do know that this is going to be 10, right? But is s a constant? No. It says at the moment in time when s is actually equal to 10, we have a bunch of information, okay? But s is a variable. The nice thing is, because we know that at this moment in time s is equal to 10, and because that plane is flying at a constant altitude apparently of 6 miles, we can, at this instant in time, determine what that length right there actually is, okay? Now, since this is a horizontal distance, and I usually set up my coordinate plane with x being on the horizontal axis, I'm going to call that x. X is also a variable. S is a variable, x is a variable, okay? And now we're dealing with a right triangle. So because s is a variable, x is a variable, but 6 is not, and I'm dealing with a right triangle, I'm going to use the Pythagorean theorem. A squared plus b squared equals c squared. So that means that x squared, if I call xa, plus 6 squared equals s squared. Okay? Now, if you go back to the rules that I gave you, remember I said always determine what's a variable and what's a constant. A, in this case, I called x. X is a variable. B, in this case, I called that 6. 6 is a constant. The altitude does not change. So I can substitute that constant in there. S is 10 at our moment in time, but it is a variable because that distance changes as the plane flies. So that's why this stays s. Okay? That is a very important thing that you have to understand. So, that's our formula right there. Let's write down the stuff that we know and maybe the stuff that we need to find. So I have s, first of all, that's going to be 10 at our instant in time. What else do I know? Is that a constant? Yes, it is. So that would be what? Good. ds over dt equals negative 400. It's negative because it's decreasing. Okay? One more thing about this little coordinate system that I set up here. Make sure that you set up a coordinate system so that you will know if something is supposed to be negative or something is supposed to be positive. There are cases where the coordinate system you set up can dictate the sign. All right. Anything else we know? And that's a constant, so we're just going to let that be. We already have it in our equation. So the 6 here is just going to be there. What don't we know? So the speed of the plane is what we're looking for, right? What is the speed of the plane? But in terms of the way we have this problem written down, what will that be? What variable will that be? Good, dx over dt. We don't know that one. Anything else we don't know? What x is. But we can figure that out, right? So x equals, we need that in order to be able to figure out what dx over dt is. So we need to solve for x, or we need to get x first. To do that, we're going to use the Pythagorean theorem, not this. We're going to use the actual Pythagorean theorem to solve for x. So, off to the side, I have 6 squared plus x squared equals, now I am going to use that 10 for this instant in time squared. So that makes this 36 plus x squared equals 100. Subtract 36 from both sides. X squared equals 64. And we square root both sides and we get x equals, technically plus or minus 8. But we're talking about distance here, so it's just going to be 8. And that's miles. Incidentally, that makes this a 3, 4, 5 base right triangle. They pop up all the time. Okay, so now we know that x is 8 miles. And now we know everything we need to know to solve this problem. So we can come over here and take the derivative. The derivative of this formula is what? 2x dx over dt. We are taking the derivative, aren't we? But we're taking the derivative of this, right, with respect to t. So if I take the derivative of x squared, I have to use implicit differentiation. The 2 comes down, so I have 2x, but then I have to tack on the dx over dt. Plus, what? That's gone, yeah. So equals 2s ds over dt. Remember, we're taking the derivative with respect to t. Okay, now what? Before we do any of that, my recommendation is to solve for what you're looking for. We're looking for dx over dt, so I want to get that by itself. And the only reason I want to do that is because it reduces the chance for making a math error somewhere else. You guys can handle this a lot easier. So I divide both sides by 2x, and I get dx over dt equals 2s over 2x, so that's going to reduce down to s over x, ds over dt. Yeah, now plug in what you have. So dx over dt, which is the speed of the plane, and that's what we're looking for, equals, s is 10, 8 for x, and then times, what? Negative 400. Okay? Well, negative 400 divided by 8 would be negative 50. So negative 50 times 10 would be negative 500. So the plane is moving at negative 500? Yeah, it is miles per hour. But what is that negative sign telling you? It's going negative according to the coordinate system that I set up. I have a positive x going this way. That's why I wound up with a negative result. So this actually is a positive 500 miles per hour. We can talk about the direction that it's flying though now. Okay? So it's moving 500 miles per hour towards the tracking station would be the complete answer.